Last month, my neighbor showed me something that completely blew my mind. He pulled out what looked like a regular phone charger, but with some copper wires wrapped around it and paper clips attached to a small magnet. When he plugged it into his smartphone, something incredible happened. He was suddenly browsing the internet without any Wi-Fi connection or data plan active on his phone. I couldn't believe what I was seeing, so I had to learn exactly how this device works and whether it could really provide free internet access to anyone. Right now, as you read these words, your body exists within an invisible ocean of electromagnetic energy that most people never think about. Every square inch of space around you contains radio waves, cellular signals, Wi-Fi transmissions, and digital broadcasts traveling at the speed of light. Radio towers scattered across the landscape pump out powerful electromagnetic signals 24 hours per day. These towers broadcast AM radio frequencies between 535 and 1705 kilohertz, while FM stations transmit between 88 and 108 megahertz. Each tower sends its signal in all directions, creating overlapping coverage areas that extend for dozens of miles. When you drive through different regions, your car radio picks up new stations as you enter and exit these electromagnetic zones. Cell phone networks add another layer of electromagnetic complexity to our surroundings. Every cell tower broadcasts on multiple frequency bands simultaneously, including the 850 MHz, 1900 MHz, and various 4G and 5G frequencies. Digital television broadcasts contribute additional electromagnetic radiation to the environment. Television stations transmit on frequencies between 54 and 806 MHz, sending high-definition video and audio signals that cover entire metropolitan areas. Wi-Fi networks create dense electromagnetic fields in populated areas. Every home, business, and public building with wireless internet broadcasts on 2.4 GHz and 5 GHz frequencies. The paradox of our current situation becomes apparent when you consider these facts. We live surrounded by electromagnetic fields carrying internet data, yet we still pay monthly fees to access this information. Urban environments contain the highest concentrations of electromagnetic radiation. Sensitive instruments can detect dozens of different electromagnetic signals simultaneously in most urban locations. Your radio demonstrates the principle of capturing electromagnetic energy from the environment for useful purposes. When you tune to a station, the radio's antenna receives electromagnetic waves traveling through the air and converts them into electrical signals. Most people throw away old phone chargers without realizing these devices contain precisely the electrical components needed for electromagnetic signal experiments. The internal architecture of standard wall chargers provides an ideal foundation for building devices that interact with ambient electromagnetic fields. Every charger contains voltage conversion circuits designed to transform 120-volt alternating current from wall outlets into lower direct current voltages. These circuits include transformers, rectifiers, and filtering capacitors that work together to provide clean, stable power output. The metal pin configuration represents the most critical feature that makes phone chargers perfect for electromagnetic experiments. These pins consist of brass or copper-plated steel that provides excellent electrical conductivity while maintaining structural strength. Most people discard phone chargers when they upgrade devices or when cables become damaged, not realizing these components could theoretically address their expensive internet connectivity problems. The USB output capability provides the essential connection method for testing electromagnetic signal processing results with smartphones and other devices. Pin preparation represents the single most critical step that determines whether your electromagnetic signal capture device succeeds or fails completely. Every successful modification depends entirely on creating proper electrical connections at the charger pins. You need specific tools to modify charger pins safely without destroying their electrical properties or damaging internal circuits. A temperature-controlled soldering iron rated between 25 and 40 watts provides sufficient heat for melting solder without overheating delicate components. The workspace setup requires additional safety considerations that protect both you and the charger from damage. An anti-static mat prevents electrical discharge that could destroy sensitive internal circuits within the charger housing. The step-by-step pin preparation process begins with examining the charger pins under magnification to identify any surface oxidation. Clean each pin thoroughly using isopropyl alcohol and a cotton swab to remove oils, dirt, and oxidation that prevent solder from adhering properly. Apply flux paste sparingly to each pin using a small brush or toothpick to coat only the areas where solder connections will be made. Heat your soldering iron to exactly 350 degrees Celsius and clean the tip with a damp sponge. Watch for proper solder flow characteristics that indicate successful tin application. Good solder creates a smooth, concave meniscus. Poor solder connections appear dull, grainy, or form convex beads that indicate inadequate heating or contaminated surfaces. The specific winding pattern that maximizes electromagnetic signal reception requires exactly 6 tight turns of copper wire wrapped around each charger pin with 0 gaps between adjacent coils. This precise configuration creates the optimal inductance values needed to resonate with ambient electromagnetic frequencies. Copper wire coils function as electromagnetic antennas through the principle of electromagnetic induction, where changing magnetic fields generate electrical currents in nearby conductors. The precise winding technique begins with securing one end of the copper wire to the base of the prepared charger pin using a small drop of solder. Start the first turn at the bottom of the pin, closest to the charger housing, and wrap the wire clockwise around the pin while maintaining steady tension. Wire gauge selection significantly affects the coil's electromagnetic reception capabilities and overall system performance. Thicker wire gauges provide lower electrical resistance that preserves weak electromagnetic signals throughout the signal processing chain. The completed device represents the culmination of precise engineering and electromagnetic theory. But does it actually work? The science behind these claims reveals some surprising truths about electromagnetic energy harvesting.